Thank you, Subhas, for discovering engineering design templates in nature's transducers. And I'm going to take you through what my thought and work in this area is like with some examples. But for many of you who are not familiar with our institute or haven't heard of it or don't know, uh, in India, we are located in Bangalore, which is in the southern peninsula of India, right bang in the center of this triangular region here, right? So this is Bangalore. And of course, Bangalore, everybody has heard of because of its IT industry. So in Bangalore is where our institute is located, and the institute is now 111 years old. It got established in 1909. We have already celebrated our 100 years, 10 years ago, 11 years ago. This institute is in a really beautiful green campus. It has, if you look at an aerial map, you will see all this concrete jungle around it. That's the city in the immediate vicinity. But inside, it's beautifully green campus. Actually, it's hard to spot buildings. It's so lush green. And in there is our Center for Nanoscience and Engineering, which is just about 10 years old. 2010 is when we established the center. And in this center, obviously everybody knows that nanoscience and engineering is interdisciplinary endeavor. We have faculty members from all disciplines: physics, mechanical engineering, electronics, materials, biology, chemistry, what have you. The centerpiece of the center is this nanofab facility, which is a large facility. It's 14,000 square feet clean room facility with class 100 and class 1000 clean room. And also there is local class 10. This clean room serves not just the institute community, but the entire country. We have now among educational institutes, we have at least 5, 6 clean rooms, significant enough to cater to the needs of researchers from other places as well. But the one that we have at IISc is the largest among all of them. And we have about 700 universities and research centers of the country that use our facility. So it's obviously a multi-user facility. The center itself has about 150 PhD students who use this facility, and then there are some other about 100 students from other departments at IISc that use this facility, and then the researchers from outside. So it's fairly comprehensive, versatile, very flexible, and large facility that is serving our needs. I'm particularly proud of setting up such a facility with my colleagues that has served incredible purpose. Okay, so now let's come to the talk that we are here for. So what I'm going to do is I'm going to look at this biomimetics versus bio-inspired engineering thought process and look at the world of insects and insect design as inspiration. I will talk about design templates and scaling and give you 2 particular examples, specific examples where we have done some work which has resulted in technology. And you will get a sense of what it is like to look at engineering design in nature and then bring it out to the real engineering design of human-made systems. So the first example is where we have been very successful, and second example, we are still waiting for success. And I will share both of that with you. So nature's engineering, as you know, all of us are in awe of nature's engineering if we pay attention to it. The famous Leonardo da Vinci said, while human ingenuity may devise various inventions to the same ends, it will never devise anything more beautiful, nor more simple, nor more to the purpose than nature does. Because in her inventions, nothing is lacking and nothing is superfluous. It's beautifully captured by Leonardo da Vinci. I couldn't agree more. And there is so much to discover, particularly for people like me who work in sensor technology and who work in micro and nanoscale sensors. Nature is the treasure trove from where we need to learn. So let's look at bio-inspired engineering. When we talk about bio-inspired engineering, what are we looking at? We are looking at principles of operation, we are looking for design templates, and we are looking for rules of scaling. It's not that nature doesn't use templates. Of course it uses templates, and there are modular units that it uses all the time. There are little variants, little perturbations of the design variables, and it gets incredible diversity by perturbing the design variables just by tiny bit. Okay, and these templates are used in all kinds of living beings. So that's, and rules of scaling. I mean, of course, nature has incredible scaling in its repertoire. Look at the flying insects. From the tiniest insects, which are as small as 100 microns or 140, 150 microns, all the way to big birds, huge birds, and in the past, flying dinosaurs. So dinosaurs. Now, those kinds of things, the scale that it covers is incredible. So, how does it scale the mechanisms is something worth looking at and understanding. Nature's design, if you look at in let's say in these three buckets, the materials, it's all organic material that nature uses, of course. That's very different from what we use. And it uses very complex transduction mechanisms. Most of it we don't understand yet. We have been scratching the surface for sure. We understand some of them, but a large part of it is hidden from us. For example, there have been a lot of work on how do we taste things or how do we smell things, but we do not think that we have it yet. We have got it yet. We are far from understanding how taste works or how even smell works, which seems like, okay, we know, but not really. Hidden templates that nature uses, they're not obvious. And you will see one tiny example I'll show you in this talk. So let's look at what biologists do. When biologists look at these systems, they look at three things: form, function, and evolution. That's their main thrust. But design is not something that biologists are necessarily looking at. Of course, I mean, there is plenty of emphasis today in systems biology on looking at how biological components or subsystems are designed, but still, the emphasis in studies are the emphasis is more on form, function, and evolution. We we want to look at if we want to look at biosystems, what we can say is the science of it is known quite a bit. What exists, how it works, we sort of know at even molecular levels. The technology is mostly molecular, and that is very, very hard for us to mimic. That's extremely hard. We don't have molecular manufacturing yet that we can do any credible things with. And engineering of these biosystems is really too complex. But at the same time, along with complexity, it has incredible elegance. And that is something that is very, very attractive for studying these systems. And you will see examples of that. So let's look at insect world motivation, all right? Um, Natural transducers, I'm talking about only this one bit of it, which is sensors and transducers in nature. Natural transducers are usually very smart. Nature's designs are extremely elegant. Design optimization is necessarily adaptive. So it's a dynamic optimization process. Energy usage is usually minimal, that we know. And the choice of transduction is brilliant. Not necessarily something that we can copy yet at the stage of development that human society is at. So we would like to discover nature's design templates and scaling laws. Okay, that's what the main motivation is. Look at this microsystem inspiration, if you will. These are images of fairy flies. These are the smallest insects that we know. Now they range in size from 140 micrometers to 5,000 micrometers. 140 microns to 5 mm. Now this is just 200 microns. The entire package system with all its sensors and actuators and processing unit and all the circuits, everything in 200 micrometers. Okay. So this is what is so fascinating, that how does nature package so much in such little space and has this incredible integrity of the entire system. If you look at the sensors that it uses, in its legs mostly for trying to find out a place to lay its eggs. It's a parasitoid. Fairy flies are parasitoids. That means they lay eggs in the eggs of other insects. Okay, so if you look at that kind of sensing capability, now these insects are so small that they are looking for eggs inside the pores of leaves. Inside the pores of leaves, there are eggs of other insects, and they are looking at those eggs to use the infrastructure of those eggs to lay their eggs. So they have to somehow go there inside the pores and find out if there is an egg there and find out the right temperature so that they can lay their eggs. So this is this hair-like structure that you see, which is already at the limit of the usual photolithography that we use in silicon processing. These are just 1 micron apart from each other and about a micron in their thickness. So these kinds of structures, which nature uses and grows naturally, is absolutely fascinating. A beautiful picture of it you can see here. Now, if I put this nature's package system in some sort of relative scale, so here is your fairy fly. Okay, I mean, of course, you can't see it on the screen because it's too small. It's about 200 micrometers, as I said. So this is what you saw. Now go 10 times higher and you have fruit flies, okay, 2 to 3 millimeters long. Fruit flies. Now they have much more developed olfactory senses, okay, because they have to smell different fruits and they have to forage for their food over there. 10 times more. So 2 orders of magnitude you are covering just in these tiny insects. And you are at honeybees, which are 10 to 20 millimeters long. If you look at them and look at what kind of transducers they're using, how many sensors they're using, we don't know yet. We don't. If you look at their design, how many sensors do they use? Some parts we know, for example, we know that the fruit fly has 40 olfactory nerve cells. Okay, so it uses 40 of them for smelling, And if you go to ants of the same size, no, they have 60, sorry. Fruit flies have about 60. And if you go to ants of the same size, they have 400. 400 distinct olfactory proteins that they use as receptors for figuring out different odors. So, when you are looking at these insects, they are worth looking at because they are still much simpler systems than, uh, larger animals or human beings, which are by far the most complex in terms of sensing and actuation mechanisms. So, if we look at these ones, our hope is that we can make sense of how these things are working, and we can perhaps copy that. So now that's nature's package system, and here is our package system. So look at how a phone has evolved into its current avatar, which is a smartphone. Why do you call it smart? What is so smart about the smartphones? What is smart about them is that they have sensors. So now this big bulky smartphone that we have right now in our hands uses about 10 to 15 sensors as of now. This is the contrast I wanted to put in front of you, right? Our prized position, and something that we pride ourselves in, smartphones. 10 to 15 sensors in this big piece of metal and plastic we have, and we call them smart. And look at those insects that I just showed you and how many sensors they have. So now let's get to our first example. I'm going to talk about bioacoustics of crickets, where we look at what I'm talking about in a little bit more detail. Okay, that let's pick up one particular actuator or transducer and study and see what it is like to study such kind of things in nature. So here is our friend that everybody is familiar with, cricket, a field cricket. And this is how it sings. Please turn around. Yeah, you can see that there is no mystery there. Okay, all it is doing is it's moving its wings. In technical terms, it's called stridulation. That kind of movement, which is sort of angular motion of the wings. That's what it is doing, and that's what is producing this rather loud sound. Okay, this is not, crickets don't have vocal cords. They're not singing, although what's coming out is their love song, but that's produced by their wings. So if you think about this as an engineered system, it's incredible. Loudest sound from a small volume. If you look at what we produce, here is your typical computer speaker at 10 centimeters. It can give you 95 dB. Human voice, normally when you are speaking, it's about 76 dB at 10 centimeters. Buzzers, 70 dB. This tiny insect, 80 dB, okay? This tiny volume compared to everything I showed you, much smaller. So from that tiny volume, how is it that such a loud sound is produced? So if you try to look at that and try to study it, now here is a captive cricket that we are trying to study here, and looking at its wing beat frequency, you see that it's about 30 hertz. 30 hertz, most of us can't even hear, all right? So the wing beat, meaning how the wing is going on top of each other, is just 30 hertz. And what you are hearing is far higher frequency. 30 hertz, if you can't even hear, its SPL is also, its sound pressure level is very, very low. But what you hear is absolutely loud, at, as I said, 10 centimeters, it's 80 dB. So not only that, now different field crickets, because what the sound that they make is their love song, they have to have unique song, because this is for attracting their mates, right? So different species of field crickets or bush crickets or all crickets, they have different song frequencies. It's like each cricket species has its own FM radio station. Okay, so it's 99.1 megahertz or whatever, 99.3 uh, uh, or 99.9. They have different frequency bands. So this spectrum allocation for songs is done naturally in nature. And how does that work if you look at this spread? So these are things that you would like to know, you would like to understand. Colleges study this, and they want to understand why their frequencies are where they are. And that's how I got started on this study, because I have an ecologist friend who gave a talk in mechanical engineering some 12 years ago, and she got me all excited about this field. Uh, so as we study these systems as engineered systems, engineering studies always like you have a box, which is a system, you have certain input, you have certain output, and you want to understand how the system transforms this input to that output. So if you look at this, you have a wing which is stridulating at low frequency, is producing inaudible sound, and what you hear is high frequency and loud sound. So what kind of transformation is the system doing, and what in the system does this transformation? What kind of design is involved in doing that? And this is what you are looking at. This is all mechanical. Uh, and I have been a professor of mechanical engineering for 24 years. So obviously 27 years rather. So I got to understand how this all works. That's what got me interested in it. So mechanism is, there is an actuation, which is wing beat. There has to be a frequency multiplier, which is taking that 30 kilohertz and converting it into 3 to 7 kilohertz that usually crickets sing in, the field crickets, that is. There are other crickets, bush crickets, and other kinds of crickets that sing at much higher frequencies too, in ultrasound range too. And where is the loudspeaker? Where is the resonator? Where is this amplifier, which is amplifying the sound to make it 80 dB? So these are the things, these are the questions that you will ask as an engineer and as a researcher, and you will start looking at details that, okay, wing stridulation is happening with muscle drive, and that is going at 30 kilohertz. And then inside this wing, inside meaning in this wing, not not inside the material, but at the bottom on the other side, at this location, there is something called a file. Okay, and I'll show you a picture. File, which has a set of teeth, and these teeth can range in numbers from 60 to 250 or so. So there is a set of teeth here, and there is a plectrum, there is a hard tissue on the other wing. So when the one wing goes on top of the other, there are set of teeth here, and there is plectrum here, which is striking this set of teeth and pushing each teeth up, okay, in this process, producing impulse of displacements. Okay, so that's your frequency multiplier. Okay, that's where one wing beat can go to 100 different impulses. Okay, if there are 100 teeth in that set. So series of displacement impulses are produced, and then inside the wing there is a small area which is called the harp. It's in the shape of a harp, as you can see here. This is roughly like looks like a harp, and that's why it is called harp. But this area is very thin compared to rest of the wing. Okay, it has it is membrane-like structure. It has veins in it, for stiffeners, but it is a membrane-like structure. And it so turns out that whatever is the impulse frequency, that impulse frequency matches with the natural resonant frequency of this harp, and the harp is set into resonance, and therefore it pumps out. Resonance means it has large amplitude motion and it pumps out so much of energy then that you get these acoustic waves, which are very, very loud sound producing waves. Okay, so that's what is going on in this whole system. Now, if you want to do this detailing, that how does it all work, what is a model, what is the design like. So you take the harp and here where the file is located, look at this SEM picture of the harp, of the file. Actually, when I saw this picture, my jaws dropped. How beautiful is that? And how intricate, sort of manufacturing has to be done, precise manufacturing has to be done to make this kind of structure. And then you have this plectrum as a hard tissue, as I said, which goes over this. So this is fascinating. This is at all in micron scales. If you look at little bit of details of what the size is, so these are the teeth, 17 microns in height, 40 microns apart, and there are many of them, number of teeth 40 to 250. So this is the mechanism, the frequency multiplier mechanism is in microns. You can see the harp thickness is very, very small, 2.7 to 8.6 micrometers. Harp area in millimeters square, and tens of millimeters square, and it lives in a package system which is in centimeter as far as length scale is concerned. That's the insect length. So it's a beautifully engineered system in scale as well. And this is what I was describing to you, that this is what happens when the plectrum goes over the set of teeth. So it is producing a set of impulses, which is what is important to remember. So now you have here a resonating structure, and you have a set of impulses which are striking it at the side of it, at the side of the structure, not in the middle. Okay, the resonator resonates and it vibrates in its first mode, where the center of the harp has maximum amplitude, but it is being excited from the side. It is just a boundary excitation or a peripheral excitation. Okay, which was a discovery, for us, that you could do it just from the boundary, because in engineering systems, you would, when you want to excite the first mode of vibration, you usually think of exciting it right in the center. So these are moving impacts, and the impacts are already, if you have 30 hertz in one beat of the wing, and you have 100 teeth, then you got 3,000 already. Okay, the impulse frequency. So you can take these wings, take their pictures, throw it in MATLAB, do the image processing, get coordinates, and you can build a model. So you can easily build a finite element model. When in all details, you can include veins if you like. You can do this fancy computational model where you have shells or shell elements for the harp, and for the thinner part of the harp, and for veins you can use solid elements. So that is done. That means your geometry is in place. You do material testing to find out what the material properties are. What is the Young's modulus of the harp that you're trying to excite? We did that, and we found the Young's modulus to about 6-7 gigapascal. It's pretty good. And then you do this impulse loading, and from the impulse loading you get a response. So when we get the response, this is what the response looks like. It's like a beat-like phenomenon, right? So this is the response that we got from our model, and this is the response which is actually recorded from the field crickets. So the moment you see that, that, hey, you have captured, my student got so excited when he finally captured this envelope, which looks like beat. And he said, I think we have nailed the model. We have got it. So I told him, Vamsi was his name, his PhD student, incredibly smart student, very hardworking, mechanical engineer, learned how to uh, get crickets from the field, how to get them to the lab, keep them happy, make them sing, make measurements on them, all of this. So I told Vamsi that, okay, you have got this beautiful envelope for sure. The response looks like what the crickets do. Why don't you do one thing? Just throw it into this displacement response into MATLAB, convert it into a voltage signal, and play it as a wave file. Play it as a sound signal, and see what it sounds like. So he did that, and this is the result. So this is coming from your finite element model. How good is that? So the moment we heard that, we all got so excited. He got excited, I got excited that, hey, this is beautiful. The model works. You do the FFT of the recorded sound, you look at the center frequency, you look at the spread, and you compare it with, the signals that are recorded. So this is recreated from FEM analysis, and this is recorded in the field, okay, for the same species of cricket that we are studying. So if you look at their FFT and central frequencies, bang on, it's excellent. Of course, in the recorded data, you will have a bit more spread because you are recording in the field, and there are other things. There are leaves, there is vegetation, there is reflection, and all that stuff. But once you get the model, and once you know that your model is working, then you are naturally excited about answering questions that otherwise it's extremely hard to answer. The spectrum allocation. How does the frequency of the song naturally differ for these different cricket species? So, biologists have tried correlating it, with area of the harp, carrier frequency, file length, carrier frequency, file tooth, carrier frequency, pronotum width, that is the top wing, uh, you know, and carrier frequency. No, obviously it's not correlated. You are trying to correlate with these things, but it's an engineered design. Okay, so you have to understand the design if you want.
Yes, yes.
Is there a question? Hello? Subhas, is that okay?
No. We'll take the questions at the end.
Okay. Okay. So we started looking at, how does the frequency vary across song frequency vary across species. Now, if you get a model, this whole power of the model is that you can do tons of simulations. You can actually create crickets that don't exist in nature at all, right? You can do that. So we took the lateral dimension of the wing as one variable and thickness of the wing as another variable, and we scaled it with the most ubiquitous cricket, which is Bimaculatus, with those species, and we started generating that what are the natural frequencies of harps of different sizes that we know that exist, and their thicknesses. And these are the contour lines of different frequencies. So when you see contour lines of this kind, it obviously reminds you of a one parameter family of curves. And therefore, you do know that there got to be some relationship between this and this, that as a parameter will pop out of this analysis. So these are the frequencies that we already know of different field crickets, the 9 different field crickets for which we have data available. Um, and they all fall right here, so what we are simulating is a much bigger design space, and these field crickets are right here, okay, very closely spaced. So the question is, why do they exist only in there, and what is the scaling? So when we looked at the scaling, thickness divided by the lateral dimension square, which is the area, in some sense, area of the harp, thickness by area. And if you look at that, then all of these crickets, you take their um, uh, data and thickness, etc., and all of it just falls out on this more or less straight line. So that's the scaling law. So the scaling that the nature is using for frequency allocation is just hidden in that harp. That how does the harp uh, scale its natural frequency in different size crickets? What is its thickness? What is its size? The shape remains the same, but the thickness and size differ, and according to that, it creates as many teeth as is required for wing stridulation. If it is a larger wing, then obviously if you drive it much faster, you need much bigger energy budget for that, much bigger power budget, and that may not be available. So there is optimization always going on, and therefore, given the size of the cricket and how much its wing will stridulate at what frequency, then the set of teeth have to be just matching enough to match the natural frequency of the heart so that it resonates. Now, so that's what the crickets are doing for producing the sound. What are our speakers like, our sound producing machines? Now, you all know how our speakers are, and surprisingly enough, even in our cell phones, the speakers that we have are not any different. It's the same magnetic speaker that we use, that are going even in cell phones. Okay, so the question is, can we replace them with MEMS speakers? Okay, can we do something different? Now, if you look at a headphone speaker, okay, the speakers that we use in headphones, it's again the same traditional speaker that you have, the same mechanism, transduction mechanism that you use. Take a look here. So here is your earpiece. Take out the ear cushion and take out the back that connects the two, right? Then look at what is inside there. If you open it up, you have a metal frame that is just to keep it together. And then if you take out the middle part, that's your speaker. There you are. Okay, that's your speaker. So this speaker and what you are holding in the other hand, okay, you will see that in parts here. This is the speaker housing. There is a housing frame, of course, that holds it all together. And this is the piece that sends sound to your ears. There is a Bluetooth module and battery, if it is a Bluetooth speaker, that is. Here is the speaker. So look at the speaker structure, okay? If you remove the top part, which is the membrane that vibrates, and it has a coil, okay, with copper wire. It's obviously a conductive coil, okay, and you have inside there, if you there is a metal piece which is the magnet. Okay, there are two metal pieces which are magnets. Look at this, you can see the vibration. We are going to actuate this at low frequency so that you can see the vibration. I guess you can see that it is vibrating a little bit, right? At higher frequencies, actually, you can't see the vibration. It vibrates, but you can't quite see because the amplitudes become very small. So here is the vibration going on. And if you look at its different pieces, you see here that you have a metal piece that is the magnet, okay, neodymium uh, magnet here, and there is another magnet surrounding this, and the space in between is where the coil goes. Okay, so now the magnetic field is obviously radial magnetic field, and then you have this current which is flowing through the coil, which is tangential. So you have got perpendicular things, right? Magnetic field, and you have got current. And when current flows, then obviously there is this Lorentz force that will push uh, this coil up, and with the coil goes the membrane. So when the membrane moves, that's what produces these acoustic waves, and that's how your speaker works. All right. So now that's the kind of thing that we have been doing so far. Now, what did we learn from the crickets? Crickets, we learned that, hey, you don't have to have this big thing in the middle to drive. You can drive things. If you drive it in resonance, you can drive it from the side. You can actuate it from the side. So we went ahead and made MEMS speakers. These are electrostatic speakers. They are just silicon membranes. That's all there is. Actually, it's not a membrane, it's a plate. So you call it diaphragm. Mechanically speaking, it's a plate because it has a stiffness of its own. The stiffness doesn't come from plane stresses. So it's a plate. And from backside, if you look at it, it has a certain depth because you have etched the silicon structure, or the wafer in which you make it. So this is what it looks like. Okay, here is your silicon diaphragm. Okay, and there is a peripheral electrode. You can see here, this is the cross-sectional view of this, and from the top it looks like this. So you have silicon everywhere. Okay, you can of course put a metal if you like as electrode on the top, but this is the membrane that this is the diaphragm that vibrates, and this part right here, that's the electrode. Okay, so this bottom silicon we are using as electrode. We apply voltage between this and the top one. This piece right here is buried oxide in a silicon on insulator wafer. So that's the insulator between the two. So you have electrostatic field between these two, and that's what vibrates it. So it's a peripheral actuation. Unlike what you see usually in electrostatic devices, that this whole thing will be complete here, and you have electrode at the bottom. That's the electrode you are using for exciting something which is free to oscillate on the top. But we have etched out this entire wafer. The handle layer is completely etched out. That gives you this depth here. Okay, and this is the key design element in the speakers. I'll show you why. Okay, so we can use these speakers, these kinds of speakers in earphones, in headphones. It's a modular design. We can even make tons of them in arrays, and we can make a singing frame out of them. So here is our MEMS speaker. Okay, and we are taking the signal from here and amplifying the signal, sending it here. Okay, sending it to our speakers and producing sound. Okay, so this is what we have done so far, and you will see some of the samples of sound from there. So how does it work? Now, electrostatic speakers are there. Bigger electrostatic speakers are there, but extremely expensive, high voltage they need. A lot of stuff which is not for mass scale production really. So now, if you look at how these things work, electrostatic forcing is what you are doing. So suppose here is your diaphragm, okay, or any structure that you want to oscillate by applying an electric field between this and this. So obviously this is conductive, or at least it has a conductive layer on it, and you apply voltage on it. Then if you apply a voltage, there is electrostatic force which will attract this and it will pull it. This stiffness and damper are just to show that yes, it's an elastic structure and it has some inherent damping in it. So when you apply the voltage, what will happen? It will go down and it will oscillate, right? If you are applying a voltage, it can oscillate about its equilibrium position. Now there is this concept called pull-in voltage in all electrostatic devices, that if this is the gap, 1/3 of the gap, up to 1/3 of the gap, your structure can oscillate very easily. You know, it goes there and comes back because elastic restoring force is large enough to pull it back and it will come back. Okay. But the moment you exceed that, then the electrostatic force wins and it just pulls the whole thing down. And that's why it is called, that particular voltage is called pull-in voltage. And at that point, you know, the two plates will just collide and you will have shorting, right? So this is something that you want to avoid. In all electrostatic MEMS devices, people are very, very aware of this pull-in voltage, and they try to keep the motion within the pull-in range so that they don't get to this shorting problem. So now look at this. You know, if this part was complete here, then 1/3 of the gap is all you could oscillate this to. Up to that, you could oscillate this membrane. But now that you have only peripheral actuation, your range for motion here is much bigger. Okay, and that's the beauty of this design, peripheral design. So look at this, take a cross section, and in the cross section, now you are able to see how the motion can be. Motion can be large amplitude motion. If you look at its side, then you will see that where the electrodes are, here is where the electrode is. The motion there is very small, but the motion here is large, right? So you have large motion there, you have small motion there, and it turns out that as much as 80 times the gap here, the electrostatic gap the electric field gap that we have, 80 times that or 100 times that deflection we can get in the center. So that's an increase of almost like 300% in terms of your amplitude of motion. 300 times, not 300%, that is 300 times. So this is the gap, and you have to only watch for 1/3 at this point, right? Not in the center. So your center deflection is huge, which can produce loud sound. So this is what we do, and we can oscillate this. This is just to give you a sense of how the sound works. This is just stripping the frequency and going through a range of frequencies. We are generally interested in up to 7-8 kilohertz. So we built this speaker, and this speaker is now able to produce sound, and I can play some samples, but this is not so good because it's coming from that speaker, then it has been put in my computer is playing it, and then you are hearing it through this audio system, then your audio system is replaying back to you. There's a lot of loss. So it's not quite what you hear is not quite as crisp a sound as you will hear if the speakers were right next to you. This is the flute. This is coming from these ultra thin micro speakers. MEMS speakers, right? So, when I heard this is Mira's work, my graduate student who has just finished. Now she's Dr. Mira Garud. So when I saw it, I certainly clapped, and I felt like clapping. So here is clapping for her. So these are the micro speakers. Okay. So what did we do so far? We studied how crickets produce this loud sound. We understood that they're using peripheral actuation, which was very inspiring. And we tried to put that kind of actuation into a MEMS scheme and are able to produce now MEMS speakers. So we are working on this technology to make it better and better. Lower frequencies are harder because we are using resonant driving, and resonance for smaller structures is at much higher frequencies. So we are right now working on, if you have good ideas on how to produce bass frequencies with these, please do get in touch with us. We would love to get your ideas. So that's the first. Now the second one, I'm not going to go through as much detail. The first one I showed you in great detail simply because we were able to take it to technology. Here we haven't been able to take it to the technology, but gyroscopes are these rate sensing systems, and you might have come across gyroscopes in your college, in your education, or at least in museums. These huge flywheels that spin at very high RPM. That was the mechanical gyroscope. Now, we have reduced all of that. It used to be bulky, 25 kg or so, to MEMS gyros, which are just a couple of millimeters in size, and low power, very, very small. But nature uses a very different structure. And although the schemes or the transduction scheme that we use based on Coriolis effect is the same, the designs are very different. So look at, this is a MEMS gyroscope, done in our lab. We work on this. This works on Coriolis effect. What is Coriolis effect? Now, if you have something moving, you have velocity. So something has a motion. And if that motion, that linear motion, happens to be in a rotating frame where the frame itself is rotating, then there is an acceleration that acts perpendicular to velocity and the angular velocity vector. Okay, so you can see that he's no more able to throw the ball to his friend because there is an acceleration that takes it away, and that's the ghost acceleration called Coriolis acceleration. So here is the ball being thrown this way. You have this bench which is rotating. So you have V. You can see here velocity. You can see the omega or angular velocity is up. So 2 omega cross V, which is Coriolis acceleration, is obviously going to be perpendicular to both these vectors, and that's sideways, and that's why the ball goes sideways when you start rotating this thing. So this is what is used in gyros, MEMS gyros. So this is a proof mass, okay, that all it means is that, okay, there is a plate-like structure, which is inertial unit, or it's a mass, okay, which you can't ignore. And these are beams that are the elastic elements that provide the restoring force. And these are comb drives that are used for actuation. So when you actuate them, it moves like this, in plane. It has in plane motion, as you can see. You are driving it like that. The moment you put a rotation on it, then because of Coriolis force, the plates also start going up and down. Okay, so if it is going up and down, then you can have this plate you can use as an electrode, and you can put a bottom electrode and change in capacitance you can use for sensing how much it is going up and down, how much is the Coriolis force. And if you know the Coriolis force, then omega is involved there, the angular velocity is involved, and that's what you're trying to sense. So this is how these things work. A fabricated device looks like this. A close-up look of the proof mass, and this spring can be serpentine spring. I mean, the suspending beam can be a serpentine spring so that stiffness is low. You can actuate it easily using these comb drives. You are applying voltage across them. So this is the kind of gyros we make, gyroscopes we make. Now look at this. This is the nature's gyroscope. Okay, so this is a fly, okay, soldier fly, and look at, there is a tiny organ here, the white one right here on the side, which is going out of phase with the wings. Okay, so this is the organ which is called haltear, and haltears are the gyros of the fly. Okay, so the haltear, uh, uh, it has a knob. It's cantilever beam basically with a end mass. Okay, so nature understands that it needs inertial mass at the end, and there are companiform sensilla at the end, which are strain sensors. So you can create a model, you can build a model of this. I don't have time, we're running out of time, so I'm just going to go through this very quickly. You can measure dimensions, you can figure out how Coriolis force is introducing bending moment, what is the stress in the haltear, what is the strain at the base, and what is the strain that is being sensed by the companiform sensilla. You can do material. You need material properties, you need geometry, you need boundary stiffness. All of these you need for building a model. We could do all of that. We could test, get the stiffness, the geometry, whether it is hollow inside or fluid field or what is it, how the haltear is inside. We did a micro CT scan to figure out what is inside so that we could do a proper model of this. And after doing all of that, we were able to figure out that just because of these two haltears at an angle, okay, at an angle, going up with large amplitude motion, the two signals that it gets, the fly gets from these two haltears, it can, from those signals, from those two signals, coming from these haltears, it can figure out pitch, yaw, roll, all of it, just by subtracting and adding those signals. Such a simple structure, and it does 3-axis sensing of rotations. Get that? That's how elegant this design is. MEMS gyros have small amplitude motion. Here you have large amplitude motion. Fixed actuation direction, varying actuation direction. Because it is in a plane and it is large amplitude, its actuation is changing. The velocity is changing direction. Single axis actuation, same actuation, multi-axis sensing. In our MEMS gyros, we usually have a single axis actuation to do single pair, single sensing. Single frequency design for actuation and sensing, two frequency design for actuation and sensing. So there are clear differences, okay? Not only that, we don't know yet how to do in MEMS that huge amplitude motion and out of plane motion of that kind. We don't know yet. I hope that we'll get there. So in conclusion, you can look at these designs in awe, and you can say that obviously nature is full of incredibly intelligent and elegant designs. That haltear as a gyro is as elegant a design as it will ever get for gyros, in my mind. Insect world is perfect for studying nature's engineering at micro and nano scales. We need to discover nature's design templates and scaling laws. We need new breed of researchers trained across biology and engineering to work on bio-inspired systems. And in this, for this work, I must acknowledge my graduate students, Dr. Vamsi Goti, who worked on the crickets, Meera, who created the speakers based on them, Rizwana Parveen, who studied the haltears in insects, with all inspiration and help from Sanjay Sane, who is a professor at National Center for Biological Sciences. Sanjay has worked on those haltears, and we have been looking at its engineering design. And Professor Rohini Balakrishnan, who is the ecologist who introduced me to this wonderful field by her talk on crickets. And the funding agencies, Defense and Ministry of Information Technology and IT. So this is what I had to share with you. Thank you very much. And I'm now open for questions.
Yeah. So thank you very much, Professor Pratap. It's such a fascinating talk. I think all of us who have actually participated have enjoyed a lot. So we'll take some questions from the audience. But before I go to the questions what already people have asked, I have just one query.
Yeah.
You talked about the size comparison,
Mm.
but one thing you did not mention is the energy part.
Yeah.
So as we know, the cricket, we do not know how much energy they spend,
Mm-hmm.
but while we make it MEMS based, how do you actually compare the power supplied from battery or source, or whether we could think of some kind of energy harvesting while the speaker moving, or creating the sound? Can we think of that?
Well, yeah, I mean, acoustic energy harvesting people have been thinking about, but generally acoustic signals carry so little energy, Subhas, that, I don't think that return on investment in terms of energy, that how much energy we're going to spend to build some system which is going to get energy from acoustic signals will work out in our favor. However, uh, I mean, that is as of now, the materials that exist for this kind of transduction I'm talking about. But this material palette in MEMS is changing all the time. And there is nothing to prevent us from thinking that tomorrow there is going to be a material which is going to have far higher, coupling coefficient in piezoelectric domain than what we have available right now. And if that happens, then it will become very easy to harvest acoustic energy, which is plenty, by the way. I mean, everywhere, all over the place. Now, energy budget, the question that you asked about insects. So energy budget is not so easy to figure out in insects.
Yeah.
Okay, simply because, of course, I mean, there are studies on this, that 30% of the energy available is reserved for songs. Okay, because they have to do different functions. Crickets have to do, all insects have to do different functions. How much is the energy budget for a particular motor activity? These kind of studies do exist, and the comparison with MEMS will not really be right comparison. We can think of efficiency, that if crickets are using so much of energy to drive something, are we able to produce similar sound with similar energy or power? And that you already know that the answer is going to be no. Simply, look at your brain, right? I mean, this example is given all the time nowadays, that 100 watts is all power that you use, and the kind of computations you do, supercomputers can't do.
Yeah.
So neural
Understood.
yeah, so that kind of thing is hard to hard to make a comparison of.
Oli, are you there online?
Yes, I'm here.
Because you have put quite a few questions. Can you actually, inquire one or two?
Nothing. It's based around Professor's sort of discussion, and that membrane being whether it's hard or soft, there's a tendency for it, if it is soft, not to be able to produce so much sound. But so it has to be stiffer, like the cone of a normal speaker, and they have this ability to remain stiff in the middle and have a excursion provided by the soft material on the edge. And,
Right.
and also the lower frequencies are delivered via an echo chamber, like a
Right. Yes.
bus box.
Yes.
That's all. I mean,
Yeah.
I saw it all in the research. It's basically there. But I was just asking whether you'll use that kind of, you know, comparison to see with MEMS especially, because these arrays are becoming popular for microphones as well as speakers,
Right.
and they're probably using some of this technology or these ideas to deliver. If you look at your mobile phone, the range and the quality of the audio is superb.
Right.
Compares with the best hi-fi systems, and
Right.
people like Bose are in it. So they're delivering quality that's far beyond what you can get out of a tiny little device like that. So I'm just saying they must be using something to enhance the audio, like to throw it out
Yeah.
from a tiny little, you know, space inside the phone, and you can get that kind of quality of sound thrown out to like it's quite loud. How do they achieve that without destroying the phone? You know?
Right, right. So, there is a lot of work actually currently going on at the MEMS speakers are still in their first generation. MEMS speakers are not yet evolved. Okay, the speakers that you are using in cell phones, it's the material is getting better and better, and also the usage of now there are phones which are using the entire screen, okay, for low frequency sounds. So it's the high frequencies are very well covered by these small speakers. It's the low frequencies where we have trouble, as you rightly pointed out, that you use that back cavity. You are using the, like what crickets do, they use burrows for amplifying the low frequency sounds. So similarly, now the designs are evolving where you are engineering the cavities or the peripheral space more and more for better quality of low frequency sound. High frequency sound is not a problem. In arrays you can make different speakers to be responsible for certain bandwidths, and those can be produced beautifully. And that's why you have, in good Wi-Fi systems, you have hi-fi systems, you have these tweeters, so many tweeters. So yes, that's where we are we are moving towards that, and engineering the peripheral space for good quality low frequency sound is right now at the forefront.
Thank you.
I think last questions will take Soma. Can you ask please? Soma, are you there online?
Yeah, thank you, Professor Rudra. It's a very nice talk. So I just curious. I mean, the way you're talking, this looks something like the drum resonator. So is it something is a similar kind of thing? Because it looks like
Yeah.
unspotten.
Yeah. It is like a drum resonator, but as I said, that the entire the bottom, you don't use the entire bottom surface for your actuation, electrostatic actuation. Okay, you are using only peripheral space for actuation. That's the difference. In drum resonators, there are all kinds of drum resonators. uh, you know uh, Still at the bottom, it's the flat surface, the entire surface at the bottom, that you use it for driving.